So remember the word ensembles that we use? What was the word ensembles, guys? Ensembles are groups of whatever, right? Ensembles could be, but in our case, because we're doing statistical thermodynamics, what are they? Molecules. If you were using information theories, your ensembles will be, that's it, mathematically identical. What? We've just done information theory, like the first lecture of information theory. Woohoo! Okay, sorry, continue. I'm sorry.
11.5.2, number of ensembles that are truly different. Clearly, the easiest way to develop statistical thermodynamics is to apply statistics to the properties of the molecules themselves. However, in general, this simple solution does not work because molecules interact with each other. Hence, the statistical arrangement of private properties in molecules does not provide any meaningful description of the macroscopic system. For example, molecules in a system have their own individual kinetic energies, but not their own potential energy, because the potential energy is of the system as a whole. So in an isolated ensemble with n members, the total number of members is just the sum of the individual particles it has, and is equal to the sum of the number of n.
So sum over all the number of particles, if I is the number of.
And the total energy E of the members that are each in their own quantum state with energies E, I, from a set of energies at any given time. It's just the sum of the energies times the number of members in a particular state. Thus, internal energy for an isolated system is given as E is equal to the sum of the total number of particles times the
energy carried by each particle. So basically it's N1E1 plus N2E2 plus N3E3, right? So all you're doing is adding the pluses in the middle, and it has to remain constant because it has to be the total energy of the whole system.
These two conditions give us the constraints on the ensemble.
Okay, so now, Faru, you're going to read the example.
Next, so suppose we have a system of 20 members where each member of the ensemble is defined to be in a particular quantum state characterized by a particular value of E sub I at any given time. Assume there are 4 possible quantum states, 1, 2, 3, and 4, with energies E1, E2, E3, and E4. Whereas respectively, as seen in table 11.4, each of the 20 members of the ensemble must be in one of these 4 quantum states. Let's assign a quantum state to each number. Each arrangement, such as given in table 11.4, represents a particular distribution of energy states.
Okay, so quantum states 1, 2, 3, 4. Suppose they have energy E1, E2, E3. And suppose out of the 20, 8 of the members are in states with energy E1, 6 are with energy E2, 4 are with energy E3, 2 are with energy E4. Do you guys remember us using the words degenerate and all of those last time we had a class? Okay. I'm sorry. Okay, continuing.
Assuming state 4 has 2 members, S and T, we have 2
Hold on.
possibilities.
State 4 has 2 members? Yes, S and T. Okay.
Order 1, S minus T, or
No,
order
S and T.
S and T, or order 2, T and S.
Mhm.
This means to arrange these members on a lattice. There are 2 factorial ways, as shown in the figure 11.8. However, since all members are identical and indistinguishable, the actual order will not make any difference. In state 3, there are 4 identical and indistinguishable members, namely O, P, Q, and R. So there are four factorial ways to arrange them on the lattice. So similar arguments can be made for state 2 and state 1, with 6 and 8 members respectively. Hence, for 20 members as separated into 4 states, the number of ensemble or lattice arrangements that are really different are given mathematically as what is that saying?
Omega?
Omega is equal to 20 factorial over 8 factorial times 6 factorial times 4 factorial times 2 factorial is equal to 1.7 times 10 to the 9.
10 to the 9. It's what,
Really?
billion? So 1.75 billion ways of arranging 20 molecules in these states. I know, right?
which we can generalize to say that we must divide the total number of members and factorial by the product of n sub I factorial, which are the number of members of each quantum state mathematically written as omega is equal to n factorial over the big pi sign.
So how do we say that?
I don't know.
So read this.
The running product of all factorials and omega is called the multiplicity.
So note this word again, multiplicity. We used that word before, right? Yeah, last time, here. No, are we ignoring that we use this word? Right here. We did that for coins.
Only new word was ensemble.
Well, yes, that is true. But multiplicity, we used it, right? For n coin. So no, again, nothing new. No, we used it last time. How can it be new when you already know it?
Not true.
Note, if we had assigned any other members to the quantum states, or if we had changed the number of quantum states, then we would get a different answer than our sample.
Good.